Thank you, Dr. Roberts. Yeah, so hello everyone. I will be presenting my research on simulating contrails. Now, as Dr. Roberts already mentioned, this is part of the NASA CLEAN project, and the goal of the NASA CLEAN project is the development of a carbon-free and sustainable aviation propulsion system of the future. And why are contrails such an important factor in this research or in this project? We already have north of 100,000 daily commercial flights worldwide today, and that leads to a contribution to the global net anthropogenic effective radiative forcing of approximately 3.5% as of 2021. Now, we can imagine that with the amount of flights projected to increase quite significantly over the next years and decades, that these numbers might go up further. Now, let's look at these 3.5% of the aviation contribution to global radiative forcing. And of course, everyone knows carbon dioxide that is emitted from traditional jet fuels, such as kerosene. And surprisingly, though, Contrail Cirrus has recently, in the recent years, been projected by several studies to have a significantly greater radiative impact compared to carbon dioxide emissions. And I will be talking about what Contrail Cirrus is and how we can go about simulating this. So that is why it's so important for the success of a project whose goal is the development of a sustainable aviation propulsion system to really understand how contrails form and then apply that to this completely new scenario of ammonia in the case of the NASA CLEAN project or hydrogen propulsion systems. So before I sort of dive into the numerics and the simulation of this, what are the different life stages of a contrail? I brought some pictures here of contrails, and starting on the left, sort of this near field area, approximately 1.5 to 2 seconds after exhaust, when that exhaust is still hot and is rapidly cooling down, and it's also very turbulent. This part is called the jet regime, and it's in the order of tens, maybe hundreds of meters in length, but diameter-wise, it's approximately 10 meters in that order. And this is also, microphysically speaking, the most complex part of the whole contrail formation, because we have a multi-phase process here. We have both liquid droplets that form as the plume cools down, and then we have ice crystals that form from subsequent homogeneous freezing. The next stage after this is governed more by the wake vortex dynamics, and I will be showing some very illustrating videos of this later, and it will become a little more clear of how the dynamics here work. But this regime is already in the order of hundreds of meters, not just, of course, in length. I mean, the length scale is always, of course, very long depending on the atmospheric conditions as the aircraft flies through the upper troposphere. But also, what's significant about this regime is that it spans hundreds of meters in the vertical direction. So a lot of the contrails in this stage that you might see actually are predominantly vertically oriented rather than spread out. The spreading out occurs in the next regime, in the so-called persistence or cirrus regime. And this is that contrail cirrus that I was showing in the earlier slide that contributes so significantly to the global radiative forcing. So this is that third regime. And for simulating these regimes, really we have individual simulations for each life stage. So we have essentially 3 coupled simulations. And our approach is doing this in a software called Meso-NH. So Meso-NH is a non-hydrostatic and mesoscale atmospheric model. And you might wonder, why do we pick a mesoscale model if we know that the jet regime is only in the order of tens of meters or so? And the reason is that in recent years, Meso-NH has actually made quite significant steps toward compatibility with smaller scale simulations. And I will be showing some of the models that Meso-NH has to offer. But then its strong suit really is the cirrus regime, and that's what it's all about in the end if we want to understand the global radiative forcing. And Meso-NH comes with a microphysics scheme called LIMA. I will be going into detail about this as well. And we have made some quite extensive modifications to some of the parameterizations in this to create compatibility with the smaller contrail scales. So we take this mesoscale model and we adapt it to the small contrail scales until the contrail grows so much that now we can actually use Meso-NH's native um, um, possibilities. So these are our initial attempts from about 8 months ago or so. So these were our first efforts at simulating contrails, and we can see here on the left, we actually started with the cirrus regime, which is where Meso-NH is really good at and what it's made for. And we can see that spreading cirrus. And then on the right, we just demonstrated some very fun little configurations. For example, what happens if multiple aircraft fly below one another and that microphysical environment impacts each other. So these were already proofs of concept that we can, in fact, simulate contrails using this software. And then the next attempt was scaling everything down, increasing the fidelity, increasing the grid resolution, allowing for the simulation of the jet regime where we have very small scales. And we can see here, this already resembles a contrail a lot more, so we can identify this quite clearly. Next, I want to walk through the so-called Schmidt-Appelman mechanism. So just very briefly, this is the mechanism that is generally accepted in the literature for contrail formation. And it really has three distinct stages. So the first stage essentially corresponds to the jet regime right after exhaust. And the aerosols that we have in the atmosphere, they activate. This is followed by subsequent condensation as that hot plume cools down. And then we have a growth of these liquid droplets. Now, at one point, the plume is going to get below approximately negative 35 degrees Celsius, and this is where homogeneous freezing starts to occur. And finally, after we get these ice crystals from the homogeneous freezing, these ice crystals may grow or shrink by deposition and sublimation, depending on the atmospheric conditions. So this is that interplay between the atmospheric conditions and the persistence of the contrail. And these were our initial attempts at actually capturing this multi-phase process in our simulation. So we can see here those three steps in that Schmidt-Appelman mechanism, and the light blue color that you can see right behind the aircraft's engine here, those are liquid droplets. And then shortly thereafter, they begin to freeze homogeneously. And then the dark blue color here, those are ice crystals. So we were able to actually simulate that multi-phase process. Now we wanted to really focus on aerosols. Because the interplay of the water vapor with the aerosols is so very important to understand the persistence of the contrail. And the difference between traditional jet fuels and ammonia, as investigated by the NASA CLEAN project, really is in the soot emissions and also the water vapor emissions. So with traditional kerosene-based propulsion systems, we have our normal water vapor emissions, but also in addition, we have soot emissions. And this soot actually serves as an ideal nucleus for condensation. So it fosters contrail formation. Now, in ammonia powered aircraft, we wouldn't have soot, but we have a lot more water vapor. And our hypothesis is that we might have so much water vapor that we actually get condensation on ambient aerosols. And this goes hand in hand with some of the preliminary findings that were also presented in some other studies, is that we will still get contrail formation even for carbon-free fuels. So how does this activation theory work that we employ for the aerosols? So if we just imagine a liquid water surface and we have some moist atmosphere right above it, let's say just hypothetically at a relative humidity of 50%, and we can ignore those equations on the right for now, then if we start increasing that amount of water vapor, so long as we stay below 100% relative humidity, nothing really happens. But then as soon as we go above 100% relative humidity, if we have a supersaturated environment, then we actually start seeing condensation into that liquid surface. And we can calculate the relative humidity by looking at the saturation vapor pressures. And on the right here, we can see some of the equations that are used by our microphysics scheme, LIMA, in Meso-NH. for determining the saturation vapor pressures. So let's apply this to an aerosol. So instead of that liquid flat water surface, we now have an aerosol, and we have some moist atmosphere around it. So this might be somewhere in the plume of an aircraft. If we do something similar, we start with a relative humidity of 50%, and then we just increase the atmosphere's moisture in this little thought experiment, then nothing happens still. Of course, we're still subsaturated. But even if we go above 100% relative humidity, say 101%, then we're already supersaturated, but we still don't see any condensation activity. And why is that? It's because aerosols have a higher equilibrium vapor pressure. So unlike a flat water body, we do not actually get condensation at a saturated atmosphere directly, only if it's very saturated. So how does this captured? The theory behind this is the Kappa-Kohler theory. And it really captures two competing effects. One of them is the solute effect, and one is the curvature effect. So we can imagine that the aerosol is very, very small. We're in the range of about 20 to 100 nanometers for these upper tropospheric regions in diameter. And at these small scales, the curvature actually impacts the tendency of water vapor to condense onto the surface of the aerosol. And then also, if we have a highly soluble aerosol, then that will tend to pull the water vapor into the aerosol. So we can imagine that depending on the chemical composition of the aerosol, we might get different activation behavior. And this is that exact equation just plotted. So what we can see here is that Kelvin effect, because it has a high curvature. And we have the solute effect, also called the Raoult effect, that captures the solubility impact of the aerosol. And what this ends up producing is one specific supersaturation that is called the critical supersaturation as star. And only if we are above that critical supersaturation is when we actually see condensation. So not if we have a relative humidity of 100% or 101%, but however much we need to surpass the critical supersaturation. And this depends on the chemical composition and the size of the aerosol. So that little blue line that I have here, I hope you can see my cursor, but that little blue line, that essentially is, let's say we start at a relative humidity of just slightly above 100%. Some of that water vapor will actually condense onto the aerosol. But as it condenses onto the aerosol, the solubility goes down, and then the required saturation increases rapidly to the point where now we all of a sudden don't have enough water vapor anymore. And this would be haze that we would find in the atmosphere. Now, if we have a much higher supersaturation to begin with, then we can actually surpass that critical supersaturation value. And once we surpass it, as the aerosol grows, as that liquid droplet grows, the required supersaturation decreases. So now we basically have a kind of like a self-sustaining condensation activity until we're back to regular supersaturation at 100% relative humidity. So the last step sort of to modeling aerosols is size distributions. So we know that, for example, the exhaust soot in a kerosene-powered aircraft is not necessarily monodisperse. We might have different sizes of those soot particles. And therefore, the approach here is to model that soot population or that ambient aerosol population using size distributions. And the great thing or the great advantage about this is that we can vary certain parameters in the size distribution. For example, for certain atmospheric aerosol species, we might know that we have a certain mean diameter, but we also have a much higher modal width. So we have a lot more smaller and a lot more larger aerosols. And we can quite simply model this. And we can also model higher mean diameters. So for, again, different atmospheric aerosols, we might have higher mean diameters. And now we link this to Kappa-Kohler theory, so that activation theory. So we see this same log normal size distribution curve, the blue curve here. And the left-hand plot shows a supersaturation of, for example, 10%. This is just a hypothetical case. And we can see this green area under that curve, that tells us essentially the amount of aerosols in this size distribution that have activated. So every aerosol has its own critical saturation and will saturate at certain supersaturation values. Now, as we increase the supersaturation to values as high as 40%, so 140% relative humidity, now much larger fractions of this aerosol population will activate, and we will get more liquid droplets. And in Meso-NH, in our Contrail module, these are essentially the different aerosols that we can model as of now. So we have a very diverse range of atmospheric aerosols that we can simply superimpose. So we can have basically arbitrary aerosol populations that we can mix from these available tabulated values. So every aerosol has its own hygroscopicity, which basically is the tendency to pull water vapor in. And then we do the same thing. This was one of our additions into Meso-NH, a local soot population. So this is because we need to be able to also model the kerosene case if we want to compare the NASA clean ammonia generated contrails to traditional jet fuels. And this is that same curve that we see, just represented slightly differently. So on the x-axis here, we have different supersaturation values. And what we see on the y-axis is the corresponding fraction of activated aerosols. And one thing I really just want to point out here is that for aircraft soot in the exhaust, we can see at the bottom here, we have a very monodispersed distribution. So most of these aerosols have the same diameter. And we can see that at saturation values of approximately 10%, almost all of them have already activated. And this is how existing literature has attempted to do this. But if we know that exhaust soot actually has a much higher range of different diameters, then for that case, we find that only about 38%, maybe 40% of these aerosols have actually activated. So that's why it's so important to model a range of diameters. So these are some of the underlying equations. For the sake of time, I'm not going to be going through all of them in detail, but I'll be happy to answer questions that you might have about these equations. So this is the homogeneous freezing parameterization that we have implemented as the plume cools down to below negative 35 degrees Celsius, and those liquid droplets begin to freeze. Now let's actually implement this. So on the right here, we can actually see some of the results. This is for the jet phase. And what we see here is, so what we've done is we've adopted a so-called temporal LES. So instead of simulating the entire contrail in its entire length, which takes up vast computational resources, we actually only simulate about 12 meters of the contrail in this stage, and we just let that 12-meter segment develop freely, as we can see here. We employ periodic boundary conditions, and then as this develops, what we can do at the end is we can just stitch the individual time points in time together to basically form this mosaic of the contrail. So this is a lot more computationally efficient, given the computational resources that we have, than actually modeling the entire contrail in its multiple kilometer length. These are the underlying equations. Again, I'm not going to be going into detail about these, but we are currently in the works of adopting a new formulation, the so-called pseudo-incompressible model. And what that allows us is it will capture the cooling of that plume more accurately. It essentially allows for an expansion of the gas. And really all I want to point out here is that it is very important for us to accurately model the plume cooling. And that is why we cannot use Meso-NH's, if I just go back a slide, Meso-NH's native anelastic formulation, because that doesn't allow for density variations, and therefore the cooling will not be sufficient. So we're currently working on adopting the Duran pseudo-incompressible model, and that will hopefully improve the cooling characteristics. So the next regime that we saw is the second sort of step or stage, and that is the vortex regime. So this regime, as we saw earlier, is essentially governed by those wingtip vortices and also the vortices from the horizontal tailplane of the aircraft. So it starts right after the jet phase ends, so approximately 1.5, maybe 2 seconds in, and goes all the way up to the breakup of that vortex pair. I will show some renders of this in just a second, and that will clear things up. So really, from the jet regime, we take all the microphysical populations, the amount of liquid droplets that might remain, the amount of ice crystals. We take the temperature fields, we take the velocity fields, and we import them as initial conditions to this larger simulation. So this is that coupling step. So this domain is approximately 400 meters long, whereas the other regime that I was showing earlier was only 12 meters long. So this is a lot larger. And the last step here is we also need to account for atmospheric turbulence. If we don't account for atmospheric turbulence, then the vortex will not break up or develop instabilities that actually impact the persistence characteristics of the contrail. So it's very important for us to actually initialize atmospheric turbulence, and that will create some of the instabilities that we can see in that initially very coherent and structured shape of the contrail. We use the MDS RFG method for this. Again, for the sake of time, I do not want to go into detail, but really what this does is we specify a certain turbulence dissipation rate at upper tropospheric levels. And then from that, it reproduces a velocity fluctuation field that we initialize our domain with. And that will lead to the instabilities. So here's a little render of some of the results that we have achieved for the vortex regime. And what we can see here is that vortex pair that descends. This happens because the wingtip vortices rotate into one another and they induce a downward momentum onto one another. And that's why this whole vortex pair rotates downward or moves downward. And then I will pause in the middle here. So approximately here, we can see, so this middle piece, the yellow tube that we can see here, that is the ice crystal mixing ratio. So that is our ice crystal population in the descending contrail. And we can see that actually we have a secondary vortex pair, a secondary wake that starts ascending. So this is characteristic of some of the contrail formations that we can actually see with our own eyes in the sky. And I will compare this to a picture in just a second. And then at the end, the contrail essentially breaks up. And now all of this ice crystal population is released quite aggressively. So this is this stage right here. And what's noteworthy about this is that if you look at the z-axis here, so the vertical axis, then we can see that the contrail has descended at this point several hundred meters. So we started at cruise altitude, which in this little render here was approximately 550 meters. And then the vortex pair descends 500 meters approximately before it breaks up. So what does this correspond to in a real life situation? So we've seen these renders, but what really are we actually seeing? So these are all of the individual frames that I've basically exported from that simulation I was just showing over the course of time. And we can see exactly that vortex descend here. Now what we can do with these is we basically just stitch them together and we get this structure that is at this point several kilometers long. And this corresponds to a contrail that looks like this. So going back to that initial picture I was showing on one of the first slides, this is how we simulated that. So we simulated the individual segments, we stitched them together to form that coherent structure of the larger scale contrail. And then if we kind of lay this over the actual photo of a contrail, then we can see that the orientation of this real life contrail is actually mostly vertical, because that's what we've seen from that vortex descent. So this is what we're simulating. And here's some initial validation that we ran for this case. So what we see here is at each altitude level in our domain, the averaged ice crystal number concentration. So how many ice crystals do we have on average at a certain altitude level? And on the left here are the results from a similar study who have also employed a microphysics scheme that was, however, that had quite significant approximations in there. Nevertheless, we can see that the general behavior and the general sort of dynamics of our simulated vortex pair very much resembles the literature. Specifically, if we look, for example, at that initial distribution here, that is about 80 seconds into the simulation. And then we can see the light green distribution here on the right where my cursor is. And if we compare that to the slightly darker green distribution on the left, we can actually see we have a very similar shape where at the top here, this volume or this area comes from that secondary wake that has ascended. Then we have the thinner part between the top part of the contrail and the bottom. And then at the bottom here, we have that all that ice population from the violent release after vortex breakup. I see there is a question.
Yes, I would like to ask that question. There is that, let's call it orthodoxy, which basically says that the contrail forming region is a relatively thin band around 30,000 feet, I think, if I remember rightly. And that's like kind of like plus minus, a couple of kilometers in width. How does that plot, which has on y-axis, distance in meters, how does it correspond with that? So where is it forming in an atmosphere?
Yeah, this is actually one of the next slides I was going to show. I was going to kind of show this or get into that. Thank you. That's a very good question. So thank you for bringing that up. So what we do, I will just go to the next slide here. So yes, the domain itself is let's say 600 meters tall, but the pressure levels in that domain correspond to the pressure levels we would find at flight altitude, let's say 35,000 feet. And then we initialize the domain. We initialize a stratified atmosphere. So we use the Brunt-Väisälä frequency that we can see here at the top. And this essentially tells us how does density change with altitude and how does the potential temperature change with altitude. And we choose values from the literature that correspond to conditions at cruise altitude. So the way we correlate the way we correlate our domain to actual cruise conditions is by matching those pressure levels. So the background pressure in the domain corresponds to those we would find at cruise altitude. So what we see here is essentially a very similar simulation, just slightly different initial conditions. We have, in this case, we're now actually simulating or we're initializing with the synthetic turbulence of the jet. And we have that stratification I was just mentioning. And what we can see here is we're also starting at very unique atmospheric conditions in this case. So in this case, at cruise altitude, what we modeled here is slightly above cruise altitude, the atmosphere is supersaturated. Below cruise altitude, a couple hundred meters below, it is subsaturated. So what would be the contrail formation in this? That was essentially the question we were asking. And what we're expecting is, and I'll just actually play the video, what we're expecting is that as the contrail descends and reaches those subsaturated regions, that is where we get sublimation. And essentially those ice crystal populations in the subsaturated regions start to diminish. And then that secondary wake that we saw carries some of that water vapor, some of those ice crystals back up to cruise altitude where it's supersaturated. So what we see here actually matches our expectations that at cruise altitude, we have a persistent contrail structure. Below cruise altitude, in the subsaturated region, we start to see sublimation and the ice crystal population and the contrail diminish. And so what does this correspond to? little segment here of the plume. So on the right here, we can see this is a quite a rare occurrence, but it can be observed sometimes. It's crow instability. So this is sort of the largest instability that we will find in these large contrail structures. In fact, they are approximately 400 meters in length scale. So that is why we picked the domain length of 400 meters. And that little slice that we have here, that little segment, is basically a part of the crow instability in that contrail structure. And that is because we initialized our domain with quite a significant turbulence that creates instabilities, and one of these instabilities is the crow instability at a wavelength of 400 meters. So now comes a slightly different and reversed or inversed atmospheric setup. In this case, at cruise altitude, we are right below the edge of a subsaturated atmospheric region. And at cruise altitude, we are supersaturated. Now, we expect this little tube structure of the contrail to descend into the supersaturated region. So we would expect it to keep growing as it descends. And then that secondary wake that ascends should enter the subsaturated region and start diminishing. And so this is kind of what we see here. So we can see the contrail slowly starts to descend further and further, but it keeps staying. I'll just pause here for a second. It keeps staying in the supersaturated region. So the ice crystals keep growing by depositional growth. And in fact, this atmospheric scenario here represents an extreme case, extreme relative humidity. And the ice crystals grow so large that in the end, we're projecting some sedimentation. So what we can see here at the very end, those vertical lines that start forming, is some sedimentation because those ice crystals in this extreme atmospheric case grow very large and essentially get pulled down by gravity. But what we can see here is that the secondary wake, it does ascend, but the contrail never starts showing in the subsaturated region of the atmosphere. So to kind of recap what we have seen this far, we started with the jet phase. This is the phase where we have our aerosol activation model here on the left. And we have what's very important about this stage is the initial cooling of the plume. And after it goes for about 1.5 seconds, and after those 1.5 seconds, we couple this regime to the second regime, the vortex and early dissipation regime that we saw just a couple of slides ago. So by coupling these domains, we are able to focus specifically on the intricate microphysics of each respective domain and each phase. But then we can, using some interpolation between these domains, we can actually couple them. And then the next step, so this is kind of where we are right now. The next step is coupling this to an even larger domain. So we couple this to an even larger domain that is going to be able to simulate the cirrus phase. And the good thing about this very large domain here, so what we can see here is essentially that transition from that vortex phase structure that we just saw into the cirrus phase. Now, this is, of course, just a render. This is what we're hoping to see in the near future. So that's kind of the next step, the cirrus phase. The great thing is that Meso-NH is made for these large-scale mesoscale processes. So really, all of our modifications to the source code and to the available parameterizations went into the jet phase and the vortex phase. And then the cirrus phase is where Meso-NH will be in its native sort of territory. And we will be able to model the surface and the heat fluxes that we get from different surface types. We can even throw some other cloud configurations in there, or other cirrus clouds, natural cirrus clouds that does not come from contrails. And then what we do after this is done in our future work, we run these coupled simulations for a lot of different and diverse atmospheric conditions. And then we can train an AI surrogate model, for example, thus bypassing all the computational efforts needed for actually running the simulation in Meso-NH. And from that, finally, we will be able to deduce the radiative forcing projections for the ammonia case. So thank you, first of all, and yeah, please let me know if you have any questions, and I'll be happy to answer them.